Okay. So the first algorithm which we'll be seeing is for the prime sieve, and let's see. Yeah. So why we use this is sometimes uh, in the part of the question we get that we need to find out the prime numbers in between the given range. Okay. So that's why we use this technique. So if we need to find out the prime number in the given range, but the problem is the very basic method, the first one. Yeah. So the very first basic method is brute force. Okay. Brute force, in which what you do is you just iterate over the loop from 1 to n and check whether it is and check for a given number whether if it's divisible, then it's not a prime number. Sorry, not from 1, from the 2. Okay, from the 2 to n, you divide every number till n minus 1. Okay, you divide that number and check if it's divisible, and then the number is not prime. Okay, but uh, still people are joining. Wait. Okay, so but the better I'll discuss one by one optimization process. So the better way which could be is if we iterate over the loop for say 2 to root of n, then also we can find out whether it's a prime number or not. Why I'm saying 2 to n? Suppose you have a number 36, and for 36 the factors are like 1, 2, 3, 4, uh, right, 6, 9, 12, 18, and 36. And this is root of n. So I'm saying if I iterate over 2 to root of n, then also we can find out that whether the number is prime or not. So why I'm saying that is because like if 2 is the factor, then 18 is also the factor. If 3 is the factor, then 12 is also the factor, and a factor of 36. Like it would divide 36. And if 4 can divide 36, then 9 can also divide 36. And 6 XOR is obviously 36. So if because they make the pairs, because if some number is dividing it, then the other quotient part would also divide that number, right? So that's why we don't need to check it till n minus 1 or n. We can directly check till root of n and specify that whether it's prime or not. So this is one part of the optimization. The another optimization, further what we can do is which is called the prime sieve method. Okay, from here the prime sieve method starts. So what happens is, suppose like n equals 20, say n is 20, and we need to find out the prime numbers in this range. So I'll explain you the algorithm. What it does is, so right, 1, 2, 3. Okay. See, so what the algorithm does is, I'll iterate from, say like 1 is not prime, we leave it. I'll iterate from that number to the last. Okay. So I'll iterate from that number to the last, and what I'll do is, uh, at the starting I'll say that all numbers are prime. All numbers It's, yeah. So I'll say that all numbers are prime, all unmarked. So what I'll do here is I'll mark and unmark. So uh, all unmarked numbers, okay, are prime. Okay, and I'll start from 2 to that number, and I'll check for the multiples of it. So what I'll do is I'll iterate over the loop. One second. So what I'll do is I'll iterate over the loop and I'll mark all the multiples of 2. Okay, so starting from the number 2, then 4 is the multiple. Wait, again, live, it's not working. Yeah, so I'll mark 4. Then 2 threes are 6. I'll mark 6. Then 2 fours are 8. Then similarly 10, 12, 14, 16, 18, 20. So in this way, I'll mark all the multiples of 2. Then I'll iterate over 3. Then what I'll do, I'll mark, okay, mark multiples of 3. So 3, then 6 is already marked. Okay, then I'll mark 9. Then after 9, 12 is already marked. Then 15, 18 is already marked, and in this way it goes on. Then I'll jump to 5 because 4 is already marked, so I'll not check for 4. Okay, so I'll come for this 5, and then I'll mark all the multiples of 5. 10 is already marked. You can see 15, 20. So in this way, whichever the number should be left in the array unmarked are the prime numbers. So this is one of the method. And for this, if I'll write what we are doing is, so we are iterating for I equals to twice of the number, then I less than equal to max of the range, and then I plus equals number. And if it is there, then I'll say that prime of I equals false. This. So what we are doing is, suppose our number is here 5. So I'll be checking the next number like 10 for 10, and then in the next time I'll add the 5 number. So I'll be checking for 10, then 15, then 20, then 25. In this way it goes on, and I'll mark those as in the prime array. Suppose that's the prime array. I'll mark them as false. So that means they are multiples, so they are not prime numbers. So in this way it goes on. But we can also further optimize it. How we can further optimize it is, say, as you can see here in the upward solution, that while I'm checking for 5, I should mark 10, 15, 20, 25, and in this way it goes on. But as you can see, 10, 15, and 20 are already marked. So I don't need to check for 10, 15, and 20. I directly need to check from 25. Okay. So this is if time would be there, if time would have been there, so I would have explained you why this happens. But as for now, you can say it as it's a property that till before n square 5 is there, so before n square all would be marked by some of the numbers before 5. Say 10, 15 and 20 are already marked by the numbers before 5, 2, 3 or 4. So they would be automatically the multiples of 2, 3 or 4. So this is a property you can say. If time would have been there, I would have explained you why. So as for now, you can say that we don't need to check for all the multiples. We'll start from n square. Okay. So now what the code would be, instead of checking from twice, so don't type it here or I'll have to disable it. So 1 second. Okay. So now instead of 2 here, yeah. So instead of 2 times of the number, now we'll be checking for number square. That is number into number. So this is how the program would go on, and this is how the optimization would work. So this is what the process of prime sieve is. Okay. So and if you talk about the complexity, like what's the complexity of it? Okay. So what's the complexity of it is? Suppose there are n okay. So we are checking. It's not working. We are removing the factors which are divisible 2. So the numbers left with us would be n by 2. Then again we are removing the numbers which are divisible by 3, then which are divisible 5, which are divisible by 7, and it goes on. As you can see, these are the prime numbers because those only would be left. So we are removing the numbers which are divisible by these prime numbers, and this goes on. So if I'll take n common, so it would be 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7, and the sum of this is log of n. So our time complexity becomes n log of n. So you can say it as approximately approx it is linear. Okay. So approx the time complexity is linear, or you can say to be specific, it is n log n. So this is how the uh, complex this program works. So if you need to,
But sir, we are checking for 1 to root n times, na? The outer loop.
no, that was the previous, 1 second. Uh, you're talking about this one. This is the third thing. 1 second. You're talking about this, right? 2 to root of n.
Yes. No, but
Yeah.
the outer loop of the this means the last approach, we can make it 2 to root n, right? Means it's not necessary to go till n for the outer
No,
loop
no.
for the last approach.
No, for the this method we need to go till max of r, because we are in this we are not checking by dividing the number. In this we are marking it out. So we need to iterate over the whole loop so that we can mark all those. If we'll go till the root of n, we won't know that the further numbers are prime or not. Like, acha, you are confusing it with, one second, I'll tell you. Yeah, so you can say that in the second approach, your time complexity is not O of n, it is O of n square. Because suppose the number given to you is n, and then you are iterating over the loop, and dividing n by each of the numbers, natural numbers till n. And if it is divisible, then it is not prime. But here, what we are doing is whatever number is given to us, we are using this loop to mark those. If there, if and after the whole program, the all the unmarked numbers are prime. So we need to check the whole loop, because in this method we are marking it, not dividing it. In the previous one we were dividing by by dividing we were checking. So we don't need to check for 9, 12, and 18, because if 2 divides, then you know that 2 into 18 is 36. So 18 would also divide. That's why we are checking till root of n. But this method is completely different. In this we are just marking it. Okay. One second. So this is the like sieve of arithmetic process. Whatever like this algorithm is called by this name, and I'll share you these links. You can see it here, and whatever I told you, that was only the part of the algorithm. You can see it here as here, from p square to n. So I have explained you the algorithm, what it is, and you can check it. And this is like CP algorithms. CP algorithms is the site which you can go on, you can check out on Google. So it contains all the like good algorithms, and all the competitive coders basically refer this site. Like, this is the best site which you can refer for the algorithms, and from beginning to like difficulty level. Okay. Then the segmented sieve, I explained you. Okay, in the segmented sieve, the like one of the optimizations was the segmented. This is not the like quite good as the sieve of arithmetic, so you can directly use this. So these three are same. Now next we will be talking about Chinese remainder theorem. Okay, so what the Chinese remainder theorem is used is, for what it is used is, one second. Okay, so for what this Chinese remainder theorem is used, like they will give you some conditions, say the number x mod say 2 is equals 1, then number x mod 3 is equals 2, and the number x mod 7 is equals to 5. And they will tell you these conditions are there, and you need to find out the number x, what the x is. Okay, so for this we use Chinese remainder theorem, and this is the very basic algorithm which everyone should know. And also they would tell you that these numbers which are given to you are co-primes. Then only this would be possible. Okay, so I'll show you these questions. These are very easily found on the. Okay, so can you guess the number which it should be, like, from these conditions? What the number would be? One sec. Yeah, so the number can be 5 because 5 mod 2 is 1, 5 mod 3 is 2, and 5 mod 7 is 5. So what happens in this algorithm is, say you would have x, one second, x mod, an array of I would be there, in which all these number would be given, and the remainder of I would be given to you. And you need to find out the number. Okay, and for that, what you can like from here, our remainder theorem starts. So you have 2, 3, and 7, and you have 1, 2, and 5. Okay, and this comes under the A array, and this is in the R array, remainder array. Okay, so for finding out the x, what we'll say is, suppose x is equals to sum of these three buckets. Suppose these are three buckets because there are three numbers, so we'll assume there are three buckets. So in the first bucket, we will like the first bucket should first bucket's x mod 2 should be like x mod 2 should come from here. Like the value of x mod 2 would come from here, and the value of x mod 3 would come from here, and the value of x mod 7 would come from here. Okay, we are saying it like that. So if value of x mod should 2 should come from here means and the rest, and from these remaining two buckets it should give 0. So for giving 0, these two buckets should be the multiple of 2, right? So we will multiply it by 2. And again for this, for giving the value of 3, and these two should be 0 for mod of 3. So if these two buckets should be 0, then we'll multiply by 3 because that should be the factor of 3. Then only its mod would be 0. Then again for this part, if the mod 7 should be 0, then these two would be the multiple of 7. So in short, what we are saying is, for this bucket, like this is the bucket of 2, so we'll multiply all the numbers 2, 3, 7 and divide by that. 2, 3, 7 and divide by 3. Then 2, 3, 7 and divide by 7. So this is what we are saying, right? So we'll call it as product array, product of I. And for finding out, what I'm saying is we just need to add those. Okay. So, but that's not the case. Again, now what we'll do is uh, say for this bucket, I'm considering for this bucket. Okay. Again, for this bucket, I'm saying that the multiple, like it was 3 and 2. So the multiple, that is 6 into, I need to guess this number, mod 7 should be equal to 5, right? Because in the earlier part, I was given here x mod 7 should be 5. So I'm guessing the number x. Okay. Suppose the number x which I found in this bucket was 6. So what I'll say is 6 into what number? That x value, mod 7 should be 5. Okay. So like for humans, we can say that the value can be mm, 2. So value can be 2. We can say that 6 to are 12 and 12 mod 7 is equal to 5. We can guess it by randomly, but computer cannot do that, right? Or for computer part, what you would be doing is you would be doing brute force and checking like whether it's true or not. But brute force is not a good solution, right? So to find out this number, what I can say is instead of this, I'll say I'll find 6 into what number, mod 7 is equals to 1. So for the solution of this, I know that if the number is inverse of 6, Okay, because by the property of multiplicative inverse modulo, so it would give me 1, right? Because it's the inverse, I'll have 1, and then 1 mod 7 is obviously 1. So, but my original solution was I need to find out the remainder as 5. So what I'll do is I'll multiply it by 5, and again here I'll multiply it by 5. So I'll find out my this number. So in short, what we can say is the whole problem, like x is the summation because we are adding all the numbers of the buckets, summation of uh, that product, one second, p of I into inverse of p of I. See, this is p of I, this is inverse of p of I into remainder of I. Okay, this is the remainder, right? Because 5 was the remainder. So to find out, I'm multiplying it by 5. So into remainder. So if I'll find out the summation of this, then I would be able to find the value of my x. So this was the whole, like how this theorem works. So I will show you in the code also. For the code, you can refer this. So this whole thing is done in the code itself. You can check. Uh, so I'm just explaining you how it's done. And again, you can check it on the CP algorithm site. The whole explanation is given, what I told you right now. So how this is done. So you can directly use these code snippets if you want to use. Okay. And the another algorithm is Wilson's theorem. Okay, so why Wilson's theorem is used is right. Suppose you need to check that 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 if that number is a prime number. Okay, so one of the methods which you can use is Wilson's theorem. So this is just a formula which you need to keep in mind, and you can directly use it. No need of any other thing. So what it states is if p minus 1 ka factorial, okay, p minus 1's factorial, if it is equivalent to minus 1 mod p, if this conditions is true, okay, then you can say that that number p is a prime number. So that's it, which you need to do. Okay, and you can see that when you'll be finding the factorial, it might be a very big factorial. Okay, and in the last session, I told you about how to find out the factorial of big numbers, right? I told you about storing the factorial in the array form. Okay, each single digits, you'll store it in the array and we'll multiply it with each of the elements of the array, right? I told you like how to calculate the factorial of big numbers. So using those two things, you can use it in your programs if you need to find out if that is a prime or not. So it depends on question to question and the complexity. Okay, for the previous one, sieve of arithmetic, the complexity is very nice. It's O of n log of n. So it's almost linear. And to solve, to use this Wilson's theorem, this is the practice problem of the Spodge. Okay, so I'll also share this with you, this link. You can check it out. This is almost like, I'll show you. Yeah, see, you can see here in the comments also. This is based on the Wilson's theorem, and to check this like if it's greater than p and all. So you can check it out, this problem. So these things are definitely, you'll definitely find these small things in the context of the online contest. So you need to know these things, okay? And if you know, then only you can apply it in the code. You can copy paste it also sometimes if you are on online platform, but for that also you need to know how this works, because it won't be the same thing. You need to make changes here and there. Okay. So any doubts till now in any of these algorithms? I can explain that again.